I'm Guy Brasseur. I'm a scientist at the Max Planck Institute for Meteorology in Hamburg, Germany. Yes, I'm essentially an atmospheric chemist. I worked many years ago on issue related to ozone in the stratosphere and ozone depletion. Then I moved to the US and I left Belgium and moved to the US and became the director of the atmospheric chemistry division. And so we worked a lot on global air pollution, a subject that is of course very important here at ECMWF. And then moved back to Europe and became director of the Max Planck Institute for Meteorology in Hamburg, where we worked on climate issues. I also led a climate service, which is kind of a bridge between science and society, so providing information, listening to the users' requirement and trying to help them. And that's basically what I did over my life. Well, this is the last meeting of essentially a 10 years long project, which has been very, very unique because it has established for the first time the capability of bringing together satellite observations, observations from the surface, from aircraft, and modeling in order to provide a way of predicting at the global scale, that's what's really unique, at the global scale, air quality all over the place in the world. The biggest achievement, and you will probably not expect that from me, is to have created a unique team of specialists all over Europe who can deal with different aspects of it, the emissions from industry, the emissions from fire, the way the meteorology disperses the pollutants, also people who have been looking at satellite data, people who have been doing measurements in the field, people who are doing forecasts or doing assimilation of data in the model. For the first time, we have been seeing the science essentially going from a research mode into an operational mode at the global scale. This is very unique. I think that what could be improved is really the visibility of the project outside Europe. It's clear that this is all supported by Europe, intellectually, financially, but it serves essentially the whole world. There is nothing like this in the US. There is nothing like this in Asia or in South America. And they all need their data because when they receive a global view of how the pollution is evolved, how intercontinental transport have moved pollutant, particles, gases from one place to another, how much this affects their local air quality. So the data is very, very important for them, but they should know more about it and they should use the data in order to downscale this information to the needs of their local population. And I think this is why I really believe that, in fact, MACC is not a European project, it is a worldwide project supported by Europe. We probably need a bit of everything, and I will tell you what I think is needed from my point of view. We need more information about the vertical profiles of the concentration. Satellite give you a global coverage, but they don't see very much detail as a function of altitude. The surface stations give you value at the station, on the ground, at the surface. But what about at 3 kilometer, 4 kilometer, 5 kilometer, 10 kilometer altitude? So to do that, we need essentially, I would say, aircraft observations, and it would be nice if we could have a fleet of commercial aircraft that would constantly measure the concentration of trace gases, of chemical compounds, of aerosol, of particle, and provide almost live a view of the three-dimensional distribution of those chemical compounds. That would be very, very useful for the models that do the forecast. It's just like the weather. You know, we want a lot of observation of the temperature, the winds. We have all that, but we need the same thing for chemical species. Now, this being said, on the analysis point of view, there is also, or the modeling point of view, there is also progress that needs to be made. And I'll give you one example. We're talking all the time about particulate matter. So how many particles do we have? How many aerosols do we have? We need to know more if these are sulfate, nitrate, if this is organic particles. So the speciation between the different type of aerosols, which is a very complex situation. This is where a lot of the progress will come in the next years. And this is where then a project like MACC or Copernicus atmosphere in the future needs to be more specific, more accurate in terms of predicting the kind of species we see, especially for particles in the atmosphere. There are already aircraft that provide measurements. In fact, Airbus has a number of airplanes equipped with instruments that can measure some of those components. And this is very important because the aircraft not only fly in the upper atmosphere, but they also take off and land all the time, so they get those vertical profile. The problem is that we have now 5 or 6 aircraft in the world to do that. We probably need 20, 30 or 40 of them that fly all over the place, including over the Pacific Ocean, including towards South America, so that we can have really a three-dimensional view of the chemical composition of the atmosphere. Now, that comes on top of what the satellite provides. The satellite provides a whole coverage, and so if you have profile here and there from aircraft, you link them with the satellite observation that you have, and also with the surface observation that we have. So we need to enhance the observing capability so that the assimilation of this data into the prediction model is improved. Exactly what we did for the weather over the last century. I think that, well, there is not one single application, but clearly more observation, more systematic observation, better way of assimilating the data in the model, in particular assimilating not only one chemical compounds, but a large number of different species that are interactive. It's a big scientific problem to do that. Number two, it's clear that we need models that provide data at higher spatial resolution. Now, it's very expensive to run a full chemical scheme at, let's say, 5 kilometer spatial resolution in a model. Nobody can do that today. So what we do, we take the global model, relatively coarse, and then we zoom into certain area where we have interest. So we should start by having regional zooms over Asia, over South America, over Africa, that are kind of connected with the global coarser resolution prediction that's done by the ECMWF IFS model. In the future, however, with bigger computers, we could probably provide a global distribution of many chemical species at very high resolution, accounting for high resolution emissions, accounting for small scale events that occur in the atmosphere. So just like for the weather, the quality of the air quality, the quality of the air composition, of the air quality forecast will improve as a function of time. And so that requires a strategy that involves better data and observational data, better assimilation system, and higher resolution, also a better representation of some of the processes in the model. So there is a lot of research that needs to be done so that the operational tool is improved. Not at all, I think. And again, take the parallel with the weather. In fact, you're right. Before World War II, everybody believed that the science had said its last word and that we had to become purely operational. And then after World War II, people realized that the quality of the weather prediction was very low, sloppy weather prediction, including during World War II when, the weather prediction was not what it needed to be for, in particular, the needs that the armies and Air Force needed at that time. And so after World War II, everywhere in the world, the university went back to the research and realized that, in fact, the operational aspect was a good requirement and need for the science to develop. The same thing should happen in air quality. It's not because the field goes more operational that there is no need for improvement, innovation, development. And in fact, the operational people will come to the research groups and the universities and the research institution and say, we have really systematically a problem in predicting this and this. There must be something that we don't understand. So let's go back to the blackboard and let's develop the science. So I think a project like MACC or tomorrow the Copernicus atmospheric service is an opportunity for the science and for the research in atmospheric chemistry. And so I believe that we will see somehow a renaissance of the research, but it will happen. Yes, something that I've never really understood is why the meteorologists, the real weather people, have not paid more attention to observation of tracers. Tracers are chemical compounds that are relatively slow reacting and are transported by the winds, by the general circulation of the atmosphere, are mixed or exchanges during convective activity, are emitted from the boundary layer of the atmosphere going to the free troposphere. The perfect, I would say, kind of system to follow, to see essentially how the dynamics works. So by understanding and looking how the tracers evolve in the atmosphere, you learn a lot about meteorology at different scales. The great advantage of chemicals is that they all have different lifetimes. Some are reacting fast, they tell you very little about the dynamics. Some are very slow, some are of intermediate lifetime, and so each of them tells you something about some of the physical processes that occur in the atmosphere. So if I had to give an advice to the meteorologist, look carefully at the trace constituent in the atmosphere. They tell you how the atmosphere functions, how the dynamics function. You will learn a lot. Oh, it's clear that the climate forcing, it is a modification of the chemical composition of the atmosphere. And so you have the greenhouse gases, you have the reactive gases like ozone, you have the aerosol, the different type of aerosol. They all interact with the radiation in the atmosphere. And so if you want to really calculate the climate forcing, the radiative forcing from those compounds, a project like the one you have been developing, MACC, and now the atmospheric service, is the perfect project. So to really calculate from day to day the radiative forcing and the climate forcing. Not only that, but you can also try to understand, for example, if you follow CO2, which is one of those tracers, how much of the CO2 gets into the vegetation, into the ocean, or come back from the vegetation and the ocean. And so the exchange between the atmosphere and land or the ocean are another aspect that where the measurements of the composition of the atmosphere can tell you something about. So chemistry is, atmospheric chemistry, atmospheric composition, is a centerpiece of Earth system science. And I'm not at all surprised that 10 years ago, Tony Hollingworth, who was a visionary person, realized, although he knew nothing about atmospheric chemistry, but we had a long conversation when he was visiting in Hamburg, for example, he understood that to monitor, analyze, monitor, and predict the Earth system, you needed to understand not only the cycles of energy, the cycle of water, but also the cycle of carbon, of nitrogen, and finally the chemical composition of the atmosphere. He took that idea and he made it a project that is now still today unique and at the forefront of the research in atmospheric chemistry, and has shown that the field can move to operational aspect with interest for users, for stakeholders, for people who need information. So Tony had really an extremely visionary conscious, and he brought ECMWF at the forefront. About 3 million people die every year prematurely because of bad air quality. So everybody gets very excited and very nervous, rightly, about climate change. Please do not forget that air quality is a crucial problem for your health. If you go to China, if you go to Africa, if you go to India, you will see exactly what it means to have bad air quality. People have health problems. People die prematurely. 3.5 million people each year. It's a huge number. So I would take the megaphone and I would say, tell your government to fix the air quality problem. And by the way, to do that, you need good analysis, good monitoring, and good prediction systems. So it's crucial. It's crucial for society, and the problem can be solved. But remember one thing, it took 50 years to clean up the atmosphere in Los Angeles. How much time will it take to clean up the atmosphere in China, in India, where 100 million of people are living? 100 million of people, billion of people are living and are subject to this issue. So we have to do something about the air quality issue, and it has to be done with the best scientists, the best program, and the best institution.